The very last lesson that we'll be studying in mechanics, momentum and impulse is linear collisions, lesson 6. There are two types of collisions that we'll be studying in this lesson: elastic and inelastic collisions. But before we look at those collisions, I want us to study a couple of concepts that are used to define these collisions. Understanding these concepts will help us to be able to easily understand the types of collisions that we have. The first concept that I want us to look at is what we call kinetic energy. Kinetic energy is defined as the energy that an object has because of its motion. So basically, this is the energy of a moving object. The fact that the object is moving, it means it has energy. We call that energy kinetic energy. Say for instance, we have a box here that has a mass m and it is moving with some velocity v. This object will have a kinetic energy K. The symbol for kinetic energy would be K, and it will be defined by half mv squared. We're basically taking a ratio of 1/2. We're multiplying that by the mass of the object, the size of the object in terms of its mass, and we multiply that by the square of the velocity. That should give us the kinetic energy of the object. This quantity will tell us the energy that defines the motion of this object. Now, this is to say that if the object were to be a bigger object, we'll have a bigger kinetic energy. And if the object were to be a smaller object, the mass is small here, we'll have a smaller kinetic energy. The kinetic energy and the mass, in that sense, they are directly proportional. K is directly proportional to m. The bigger the mass, the bigger kinetic energy. The smaller the mass, the smaller is the kinetic energy. They grow and decrease by the same ratio. The other observation here that we have to see is that if the object moves with a high velocity, so this velocity is much larger, then we're also going to have a bigger kinetic energy. And if the object moves with a smaller velocity, it has a small velocity, well, not velocity but speed, because the V here stands for speed in the formula. So we'll have a smaller kinetic energy as well. Again, we can see that direct proportion relationship between kinetic energy and the velocity, to say the kinetic energy is directly proportional to the velocity. They increase or decrease by the same ratio. The other thing is that kinetic energy is measured in SI units called joules. We measure energy in joules. Well, any energy in general is measured in joules, and so kinetic energy as well is measured in joules. The SI unit for kinetic energy is joules. If we were to have, let's say, two objects that have the mass m1 and m2, because they are two different objects, and they also move with, say, the velocity is v1 and they have the velocity also v2, to say this is the velocity of m1, the block, the first object here, and this is m2 and this is the velocity v2 of the second object. which is like the ball in this case. We then have two interacting objects, because this object at some point maybe they may collide with each other, or they interact with each other in this motion. And we defined that in our previous lesson to say that it is going to be called a system. Such a configuration is called a system. We said a system is a group of interacting objects. And indeed, in this example, I have two objects, which basically two would mean it's a group that are interacting with each other. Now, within this system, we do have the kinetic energy for this object here, the first object. I'll call it K1 to mean that it is the kinetic energy for the first object. It will then be defined as 1 over 2 m1 v1 squared. We basically taking the definition of kinetic energy here and using it within this system for this object to say it will be given by K1 half m1 v1 squared. The same is true if we were to look at the kinetic energy of the second object. It will be given by K2 is equals to 1 over 2, and we have here m2 v2 squared. This would be the kinetic energy of the second object in the system. Remember, this is the system boundary, the way we defined the system in our previous lesson. Now, because these objects are within a system, we then can find the total kinetic energy of the whole system. We can look at this system as one thing. Remember, when we have a system, sometimes we tend to look at it as one thing. So we can find the total kinetic energy of the entire system. Total simply means that we sum the quantities that are in a system. In this case, we are summing the kinetic energy of the system. We add the energy in the system here. And we said we use the symbol summation when we do the addition or the sum, or to find the total. So it means I'm going to have the summation of K, right, meaning kinetic energy of the system. This would mean the sum of the kinetic energy of the system. And it means I'm simply going to have kinetic energy of the first object, which is this, plus kinetic energy of the second object, which is that. But we are saying here that kinetic energy of the first object is given by half mv1 v1 squared, and kinetic energy of the second object is given by half m2 v2 squared. So this represents the total kinetic energy of the system. It is simply the scalar sum of the kinetic energies of each object in the system. We're really adding the kinetic energy of each object in the system. It's a scalar sum because kinetic energy is a scalar quantity. Kinetic energy is a scalar quantity. So we are adding scalar quantities here. That is to say, kinetic energy only has the magnitude. It doesn't have a direction. We can't say the kinetic energy is 2 joules to the left. We can't say that with kinetic energy. It only measures how big does the object, how big is the kinetic energy of the object, how big is the motion, the energy of motion of that object as it moves. Because we said it's the energy of motion, and that will be defined by how big the mass is and the velocity is for us to get the kinetic energy, because we said it is directly proportional to both the mass and the velocity. The other piece or element of knowledge that we need to understand is a law that we call the conservation of energy. The conservation of energy, the law of conservation of energy. This law, perhaps maybe I should write this way here to say the law of conservation of energy. This law states that energy cannot be created, no destroyed. It can only be converted or transformed or transferred to other types of energy or other forms of energy. So what we're saying here, we're saying we cannot get into the lab and create energy and even destroy energy. One cannot go and say, I'm busy creating or destroying energy in the lab. We cannot do that. But we see that energy can only be converted. It can only be moved from one form to another, one type to another energy. Now, to explain this, I will use a diagram here where I have a truck. This truck starts off being here at this point A, and then it moves to point B. So basically it will move to point B and come here at point B. But for that to happen, there's a couple of things that we have to observe in terms of energy. The truck has a tank here. It has a tank here, which this tank, inside the tank, there's petrol. There's some form of fuel that we have in there. And the truck also, has a battery. Usually maybe it will be somewhere there. It also has a battery. So we'll also have a battery in the truck. This means that we actually have what we call chemical energy from the petrol and the battery. It is stored inside the tank and it is stored inside that battery, the chemical energy. When the car is switched on, a couple of things will happen here. It will start making sound and it will also move because now it is on and then goes to point B. So we're saying here that this truck will have the mass M and it will move when you switch it on so that it has the velocity V. So at some point when it gets to point B, we still have some form of velocity here, and of course it has the mass. Now, you have to notice that all this sound that is making, the velocity that it now attains, is actually fed, or it comes from the petrol and the battery that is inside the car. That means we are using up the chemical energy and converting it to other forms of energy. So in this diagram, you can see that there will be the lights that switch on in here. That means some of the kinetic energy that we started with will be converted to light energy, because I can see that there is some form of light energy here that we're going to have. But this light, for it to also occur, we need some form of electricity. That means some of the chemical energy will be converted to electrical energy. And the fact that the car is actually moving, it has the mass and the velocity, would tell me that here, this two combination also gives me the kinetic energy. Because now it has some form of motion, and we said the energy that defines motion is called kinetic energy. The other thing that you have to observe is that when all these mechanics are taking place in here, there will be some form of sound energy that the truck is actually producing. There'll be a sound that is propagated in the air, right? So there'll be some form of sound as the car is actually moving. And then we also have sound energy. There could be also some heat energy. A lot of components or elements in the car will start heating up, giving us what we call heat or thermal energy. All these energies that are now appearing when the car is actually moving, they come from this energy. It means this chemical energy is then being converted to all these forms of energy. That's why eventually when you look at the tank and you look at the battery, they will actually be used up. You'll find that we had full tank when we started here, but now we have, half empty of the tank, or the tank is empty. It will be depleted at some point. The battery as well will be depleted as time goes on, because that energy is being converted or transferred to other forms of energy to then make the car to be in motion and operate. That's basically what the law of conservation of energy says, to say energy moves from one form to another form. Very important to be able to understand these energy transformations for us to use in our understanding of collisions. Now, let us look at the two types of collisions that we have. I think we have a good background to understand these collisions. The first one is called elastic collision. If we have two objects that are, say, moving towards each other, I'll say M1 and I'll say V1 initial, because it's going in that direction. Let's say we have another object here, which we call M2, and it is moving with some velocity here, V2 initial. Obviously, we can see that this becomes a system because I have two objects that interact with each other. They will collide with each other. So this would be before the collision. Then eventually they'll collide with each other. Let's say after the collision, I then have this first object M1 moving in that direction with a velocity 1 final, because this is after collision, so the velocity would change. And let's say this also big object happens to then move also in the opposite direction with velocity V2 final. Obviously, before collision, it should be clear that we have total kinetic energy here in the system, so that our kinetic energy, the total kinetic energy of the system initial, would be given by 1/2 M1 V1 initial squared plus 1/2 M1 V1, well, M2 here, initial squared. And after collision, because the velocities has changed, we are going to have the total kinetic energy of the system final, right? We need the sum of the two kinetic energies here to be 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. I'm basically just adding that to find the total kinetic energy as we define total kinetic energy. Now, in an elastic collision, what actually happens here is that the total kinetic energy of the system before collision, it is exactly the same as the total kinetic energy after the collision. In other words, the total kinetic energy is conserved. It's the same number. If I get a energy of 100 joules here before collision, when I add the kinetic energies. I should also get 100 joules here after collision when I add my kinetic energies. So it is the same number, it is constant, it is conserved. So we're saying here that the total kinetic energy of the system before collision must be equal to the total kinetic energy after the collision of the system. And this can be expanded really to half m1 v1 initial squared plus half m2 v2 initial squared, and is equals to 1 over 2 m1 v1 final squared plus 1 over 2 m2 v2 squared. I don't know why I like to write m1 again there. So in expanded form, this is how it would look like. Now let's zoom in carefully to see what is happening here, because remember, we have the law of conservation of energy. Why is this energy not changing when these two objects actually collide? Right? Why is it the same? What makes it to be the same? Well, what this means is that you would find that perhaps the kinetic energy here before collision is the largest, right? Meaning we have a high velocity here, maybe also a high velocity here, so that when I put a big velocity and a big velocity here, I will get a big value here and a big value for the kinetic energy of the second object. As a result, when I add them, I then get a big initial kinetic energy, right? But what happens now is that after collision, you would find that maybe one of the velocities here becomes small, meaning I have a small number here of kinetic energy. But when that happens, we have the largest velocity. Maybe this moves at a very high speed after collision, giving us a big kinetic energy. So that when I add these two values, they still give me the same value I started with at the initial situation before collision. So what I'm saying is that the transformation that happens here of energy, the energy is still being converted here when the collision happens, but it happens within the system itself. So this kinetic energy was big before we started, both of them were big, but here this becomes the smallest and this becomes the biggest, so that when I add the two, I still get the same number that I had here, but our kinetic energies here are the ones that are changing. So that means if I have a big value here and I have a small value here, it means this kinetic energy here used to be big and here it dropped. But here I had some kinetic energy, but now it is the biggest, it has increased. So that when I add these two, I get the 100 joules as I made an example last time. But still, even here, when I add this and this, I still get the 100 joule. So the kinetic energies are being transferred within the system. It means when this collision occurs, our energy is being converted to kinetic. We're moving from kinetic energy to kinetic energy, but of object 1 to object 2. I hope that makes sense. The other thing that I wanted to share on this is that this type of collision is not restricted to two objects as I've done in my example. You can have more than two objects, so I can add the kinetic energy of the first object, the second object, the third object, and so on. These dotted lines would mean we can add as many objects as possible. A system, remember, it's a group of objects, and group could be as many objects as we can. And even this side will have kinetic energy of the first object, second object, and we can have infinitely many other objects. Usually you will get only 2 objects, maximum 3 objects in your exams. And the other thing that I wanted to touch is that because the kinetic energy is being transferred within the system as kinetic energy, as we explained, it then means there are no any other forms of energy. In this type of a collision, we cannot have sound, because immediately these two collide and we detect some sound, then we have sound energy. It means some of the energy will be converted to sound. So because it is not converted to sound, there's only kinetic energy to kinetic energy here, there shouldn't be sound. And the other thing is that there shouldn't be any deformation. Deformation means a change in shape. So when these two collide, they cannot change shape. This cannot change shape and be like that during collision, because if it changes the shape, it then means there have to be some form of sound. For you to deform something and change its shape, there must be a form of sound, and also there must be heat energy to deform something, because there'll be a friction involved when you change the shape of something, and that friction will cause some form of heat. So there shouldn't be any form of deformation or heat that is produced in this collision. There's only kinetic energy being converted to kinetic energy within the system. The other type of collision that we study really is called inelastic collision. Now, in an elastic collision, we suppose, if we do the same example to say, let's say we have an object with mass 1 and it is also moving with some velocity 1 initial, and it then collides with another object that has the mass m2 and is indeed moving with some velocity v2 initial. This is to say it is before collision because they're coming towards each other. Now, the two, let's say they collide here. We have M1 and we have M2. So this is during collision. And after they collide, let's say our M1 moves with some final velocity here, V1 final. And our M2 moves in that direction with some final velocity v2. In this type of a collision, what happens is that the total kinetic energy before collision, it is not the same as the total kinetic energy after collision. In other words, if we look at the sum of kinetic energy before collision here, we will have half m1 v1 initial squared plus half m2 v2 initial squared. And we're saying that total kinetic energy before would not be equal to the total kinetic energy after, the final kinetic energy here of the system. So we're saying in this type of a collision, the kinetic energy initial should never be equal to the kinetic energy initial. They are not the same. So now, if I add the kinetic energy of the first object to the kinetic energy of the second object, it will give me the total kinetic energy of the system before collision. Let's say I get 100 joules, right, for example. Now, in this one, I'll add the total kinetic energy of the first object to the total kinetic energy of the second object. And then here, suddenly, I get maybe 80 joules. Do you see that these two are not the same when I look at or compare their kinetic energies before and after collision? This one has reduced by about 20. It is small now after collision. Now, what could happen if we apply the law of conservation of energy? What could have transpired here is that during the collision here, these two objects, when they collide, they will make a sound during impact, so that we have sound that is produced, and that means some of the kinetic energy we started with here will be converted to sound energy. It will then go out of the system as sound energy. And also when they collide here, the impact, oftentimes you'll find that there will be some sparks that can appear here. You know, sometimes when objects collide, you will see sparks appearing. That means here we then have light energy. We'll look at that as light energy, because for sparks to occur, it means they are propagating light waves. And if you see sparks as well, that is because of heat, the friction that happens when these two collide. It means also here we'll have some form of thermal energy, what we call heat energy. There's a little bit of heat energy, small amount of heat energy that happens. And in fact, some of the collisions, when they occur, a fire can also erupt because of this heat energy that occurs there, that is denoted as well as sparks, right? So that means our energy here is being reduced from that 100 joules, and the 20 joules that we said will be out of the system, because remember I said, let's say here we're going to have an 80. It means a total of 20 joules will be shared in these energies. Maybe 5 will come here, 2 will come here, and the remaining would be the light energy. Now that's why the two energies, when you compare them, the total kinetic energy before collision and after collision, here it's final, it's not initial, it's final here. The two kinetic energies, when you compare them, will not be the same. It's because some of the energy has been converted. And very important, energy is not lost or destroyed, right? Remember, our law says it can only be transferred from one form to another, so it is being transformed to other forms of energy. By default, we should see that an elastic collision would then have heat, sound, light, and also change in shape. There'll be some form of deformation, because sometimes you'd find that this object will be deformed a little bit here, and this one also can be deformed. It can change in shape. Now, the other thing that I wanted to mention here with elastic collision is that sometimes we have what we call a totally inelastic collision. This is a type of collision where objects collide and stick together. After collision, they stick together, and we've seen these types of collisions in our examples above, and also when we explained the law of conservation of energy. Objects sometimes collide and stick together. When that happens, we call that a totally inelastic collision, right? It's completely inelastic, and in that collision, definitely all these characteristics we should see sound, we should hear sound, there will be some form of heat energy, light, and also a change in shape, because for objects to combine and stick together, they must change shape and become one thing, combine and be one thing. And the other last part is that in both elastic and inelastic collisions, the total momentum of the system is a constant, is always conserved, provided that the system is isolated or is a closed system. So whether the collision is elastic or inelastic, the total momentum will always be a constant if the system is a closed system or is an isolated system. So very important to be able to see that the collision can be elastic, but the momentum is always conserved. It can also be inelastic, but the momentum will also be conserved. The only condition to the momentum being conserved is that the system has to be isolated, meaning there should be no net external forces acting in the system. We will now jump into questions to practice how to use this knowledge of linear collisions. Stay tuned for the first question.